Welcome to the fourth lesson of the sixth module, which is on stresses and beams part 4. In fact, in the last lesson we have discussed some aspect of shearing stress in beams, and we have looked into the effect of shearing stress in a beam having rectangular cross section. Now, we are going to discuss in this particular lesson that what is going to happen if shear stress acts in a beam having cross sections other than the rectangular ones, like circular one or the T sections. Hence, it is expected that once this particular lesson is completed, one should be able to understand the concept of shear stress in beams of different cross section, understand the effect of shearing strain on longitudinal strain in beams. In fact, we have discussed the effect of the bending moment which is acting in a beam, and we have calculated the stresses corresponding to that, and we have seen that the beam is subjected to the longitudinal strain or the strain in the longitudinal direction of the beam because of the effect of this bending. Now, what is the consequence of the shearing stress which is acting in the beam on this longitudinal strain, that we will be looking into. Also, one should be in a position to evaluate shearing stresses in beams of different cross sections for different loadings. Hence, the scope of this particular lesson includes, as we do the answering of the questions which we have posed in the previous lesson, that we will be doing it, and in the process we will recapitulate the aspects which we have discussed in the previous lesson. Also, the concept of shearing stress in beams of different cross section is included in this particular lesson. The effect of shearing strain on longitudinal strain of beams, and this lesson includes the examples for evaluation of shear stresses in beams of different cross sections. Now, let us look into the answers of the questions which were posed last time. The first question given was, what are the assumptions made in deriving the shear formula? Now, as you remember, in the previous lesson we have discussed that how to derive the shear formula, and consequently you had seen that we had made some assumptions in that, and the assumptions are like this, that at any cross section when there is the shearing force acting, we assume that the shear stress is parallel to this shear force. That means, in this cross section the direction of the shear stress is in the same direction as that of the shear force, and this is what is done. The shear stresses acting on a cross section are parallel to the shear force acting in that particular section. Also, it is assumed that shear stresses are uniformly distributed across the width of the beam, and this is very important, that at any point along the depth the distribution of the shear stress along the width is uniform. And based on these assumptions we had derived the shear formula, and as you had noticed that on a particular element we have the vertical shear and the complementary horizontal shear, and this is the state of stress at a particular element based on which we had derived the shear formula. So, basically these are the two main assumptions based on which we derive the shear formula. Now, what is the limitation of shear stress formula? Now, that you have seen that while calculating the stresses in a beam due to the shear force, we have used the shear formula which is V q over I b, and consequently we calculate the shearing stress at any point along the depth. Now, is this particular formula applicable for all kinds of beams, or there are certain limitations on that? That is what let us look into. Now, what we had assumed, as you have just now seen, is that the distribution of the shear stress across width, we are assuming that as uniform. Now, when we are dealing with a beam of rectangular cross sections, now this accuracy of this particular shear formula depends on the height to width ratio. That means, if we have a beam with rectangular cross section having the width b and height h, so the accuracy of this particular formula depends on this ratio of h by b. Now, if h by b is larger, what means is, for a constant value of h, if b becomes smaller, so the accuracy of the shear formula increases. That means, if h by ratio is higher, we get accurate result using this shear formula, or in other words for a particular depth of h or for a constant value of h, if you have lesser width of b, then the accuracy will be better using shear formula, and that you can understand from the concept that we are assuming shear stress is uniform over the width of the beam, and hence if we have a smaller width, it is expected that your accuracy of the shear stress formula will be more. But if you have a wider beam, that means if you are going towards more of a square beam with square cross section, then you will be losing the accuracy if you use this shear formula. Hence, this aspect should be kept in mind. This is one of the important limitations of shear formula. Also, from this it appears that then the shear formula to be more effective or to be applicable, the edges of the cross section must be parallel to the y axis. Or what does it mean is that if we have a section, this is the y axis and this is the z axis. Now, for rectangular or square sections we have these edges are parallel to y axis. Now, if you have a section say something like a triangular one, or if you have a section which is a semicircular one, for this kind of section the edges which are not parallel to the y axis, these sections are cannot be, or the shear stress formula cannot be used for evaluating stresses for such cross sections. So, this is one of the prime limitations of the shear formula. Thirdly, the shear formula is applicable for the prismatic beams only. That means, if a beam has a taper, it is not uniform in its cross section, then you cannot use this shear formula for evaluating the shear stress in the beams. So, these are the main limitations of shear formula. So, we can use shear formula for evaluating the stresses, shear stresses in a beam when the edges of the cross sections are parallel to y axis. And for other sections like a circular one for which the edges are not parallel to y axis, we resort to some means, or the shear stresses for such sections can be evaluated by going for other rigorous theories, which we are not going to discuss at this moment. And the third question posed was that what is the value of shear stress in a cantilever beam subjected to moment at its tip. Now, this is the question which was posed, that you have a cantilever beam, that means the beam which is fixed at one end, and if a moment m acts at the end of this particular beam, then what is the value of the shear stress in such beam? Let us assume the cross section of this beam is a rectangular one. Now, if we draw the bending moment diagram as we have done in the past, we can remove this support and we can write down the reactive forces, and thereby we can evaluate these reactive forces, the vertical force, the horizontal force, the moment based on the external moment. And if we do so, you will find that the vertical force will be 0, because the summation of vertical force equals to 0, and there are no external vertical forces. So, vertical reaction is going to be 0. Again, summation of horizontal forces equals to 0 will give the value of h equals to 0, as there are no horizontal forces on the beam. Now, only thing is that the moment will be equal to the externally applied moment, and at any section we take, and if we draw the free body diagram corresponding to that particular free body diagram, the value of the internal moment is equals to the external moment, and that is how we get a bending moment diagram which is a rectangular one. That means, everywhere we have a constant moment. Now, if the moment direction is reverse, is in a clockwise direction, we will have exactly the same result, only thing the moment will be negative instead of a positive one. Now, if the moment, or since the moment is constant everywhere, so you can make out that the value of dm dx, which is nothing but equals to shear force for constant moment, dm dx equals to 0, thereby the shear force equals to 0, and hence the shear stress will be equals to 0, because shear stress is equals to V q by I b, and since V is 0, so the shear stress is going to be 0. So, this is what is the answer of the third question. Well, now let us look into that what is the effect of the shearing strain on the longitudinal strain. Now, let us consider a cantilever beam again, the cross section of which is a rectangular one, Now, as we have seen that the shear stress in such section varies parabolically, and the shear stress tau, since it varies parabolically, the shearing strain gamma, which is equals to tau by g, also varies parabolically. So, at the neutral axis we get a shearing strain which since the stress at that neutral axis is higher, the shearing stress. So, corresponding shearing strain also is high. Now, if we consider a beam, a cantilever beam having rectangular cross section and is subjected to loads, so that everywhere you have the same shear force V, then the cross section is going to have deformation, because earlier when we had derived the bending formula, we had assumed that the plane sections remain plane even after bending, and it becomes the perpendicular to the axis of the beam. Now, because of this shearing strain, this distribution of the shearing strain, wherein the shearing strain is 0 on the surfaces and has maximum value at the neutral axis, the section is going to warp in this particular form. And at this point, since the shearing stress is 0 and correspondingly shearing strain is 0, the here the shearing there will not be any deformation. So, this particular line will be perpendicular to the surface, and maximum deformation will occur at the neutral axis point. Now, for constant shear force, all the sections are going to warp in the same form, and hence the strain in the longitudinal direction will have no effect because of this shearing strain, and consequently, as we have seen that the bending formula which we have derived from the longitudinal strain criteria also will remain unaffected. So, if you have a beam where the shear force is constant and consequently the warping which we are going to get are uniform in all cross sections, it does not have any effect as such on the longitudinal strain, and consequently we can use the bending formula even if the bending moment is not uniform, that means it is along with the shear. Now, also it has been observed that when we go for a detailed investigations for such warping because of the non-uniform shearing stress, that means if the shear stress is not, or the shear force is not uniform along the beam, if there is varying shear force, then the warping will not be constant in all cross sections, and thereby there will be some amount of changes in the longitudinal strain, but the change in the longitudinal strain is not to the extent, or the accuracy level is not jeopardized to that extent, and hence the bending formula can be used for beams which are subjected to moments along with the shear. Now, here you should be in a position to appreciate that when we had evaluated the bending formula, we had considered only the pure bending, and consequently we had calculated the bending stress. Now, that as we know that when a beam is subjected to loads, it is not only subjected to bending, but shear force also is associated with that. Now, if you have, in fact, such kind of bendings we call as a non-uniform bending. Now, when you have this bending along with shear force, there though the bending formula has been evaluated exclusively for the bending moment alone, we can use the bending formula for such beams also where we have non-uniform bending. That means, if the bending is associated with the shear force and the accuracy level is not jeopardized to a great extent, and hence is justified to use the bending formula even if there is warping due to the shearing stress. Well, now let us look into that if the cross section of the beam is a circular one instead of a rectangular one, then what is the consequence of this particular shear formula which we have derived earlier, which is tau equals to V q by I b. Now, here let us consider a circular section, the radius of which is r, and the shear force which is acting is in the cross section is in the vertical direction. Now, as we have assumed earlier that the stress direction of the shear stress also will be in the direction of the shearing force, number 1. Number 2 is that the shear stress distribution across the width is uniform along the depth of the beam, wherever we take any point, the shear stress distribution is uniform over the width. Now, when we are talking about the circular cross section, then as you know, on the surface of this particular beam there will not be any stress. So, on the radial direction there will not be any stress and that will be 0. So, the stresses which we will have all is in the tangential direction, and hence these stresses are no longer going to be parallel to the y axis. So, it is very difficult to use this particular formula, or in fact this particular formula cannot be applied in evaluating the shear stresses in this particular zone. However, if you look into in this particular position, which happens to be the neutral axis of this particular cross section. Now, here since at this particular point or along this diametral weight, the shearing stress is all are in parallel with y axis, then we can compute the shear stress only at this particular location. Now, as we have seen in the case of the rectangular one, that the shear stress is maximum at the neutral axis. Hence, we say that for at the neutral axis the shearing stress is maximum. So, and that is true for this circular section as well. So, at the neutral axis position, which is along the diameter, is the maximum shearing stress that is occurring. So, if we compute the shearing stress value at the neutral axis, we are going to get the maximum value of the shearing stress in the circular cross section. And since along that particular diametral weight, we assume that the shear stress is uniform over the diameter and they are parallel to the y axis. Hence, we can use the shear formula exclusively for that particular location, and we cannot use the shear formula in the upper and the lower part using this particular expression to evaluate the shearing stress. So, what we can do is that we can use the shear formula for evaluating the maximum value of the shearing stress in this circular cross section. Hence, the value of the tau max we say is equals to V q by I b, for which q is equals to the section above this particular cross section where we are evaluating the shear stress. So, we take the upper half of the area for evaluating the value of q. So, q is equals to a y bar, and a of the upper half is equals to pi r square by 2, and the distance of C g from the neutral axis is equals to 4 r by 3 pi. So, this is what is used here. So, this is the value of q. Also, the value of I is equals to pi r for r to the power 4 by 4, and b is the diameter which is equals to twice r. So, if you substitute the value of q, I and b in this expression for tau max, we get the value of maximum shearing stress as 4 by 3 times V by A. So, V by A, as you can recognize, we have designated this as the average shear. So, tau average is equals to V by A, and that multiplied by 4 by 3 will give us the maximum shear for the circular cross section. Hence, though we cannot use the shear formula for evaluating the shear stress over the entire cross section, which is quite complex, we can evaluate the shear stress or the maximum shear stress at the neutral axis position using this shear formula. Now, this can be extended to the cross section which is like this, which is an annular section or a tubular section, where this part is open, and let us assume that the outer radius of this is r 2 and the inner radius is equals to r 1. Now, if we have that, as we have seen that the moment of inertia I is equals to pi by 4 r to the power 4. So, if we subtract the internal circular part from the external one, we get the I of the annular part. So, this is pi by 4 r to the power 4 r 2 to the power 4 minus r 1 to the power 4. Q is 2/3 r cube, and in place of r we are substituting r 2 cube minus r 1 cube. B is equals to twice r, and we are substituting for r as r 2 minus r 1, the external radius minus the internal radius. And if we substitute this value of I, q and b in the expression for maximum shear stress. So, in this case also we compute the shear stress at the neutral axis position, and which is the maximum shear stress, and which is given by this particular expression, the 4 b by 3 a, which is that of solid circular section, and gets modified by this particular parameter, where r 2 and r 1 are the two radii of the external and the internal core of this particular circular section. So, the values which gets modified 4/3 by V A is this r 2 square plus r 2 r 1 plus r 1 square by r 2 square plus r 1 square, where area is equals to pi times r 2 square minus r 1 square. Now, let us look into another type of cross section, that if the cross section of the beam is similar to that of an eye. Now, if you remember, while discussing the bending stress, we had discussed that if we take a beam, the section of which, if we have two rectangular sections placed at a distance apart, then that contribute more to the value of the moment of inertia, and thereby we get the maximum effect in the bending stresses. Now, the question was that two rectangular strips placed at a distance apart, how they are going to be utilized as a cross section. Now, subsequently we had looked into, if these two particular rectangular sections are connected by a vertical strip, then we can use that section as a beam cross section, and that turns out to be most economical section when we talk about the transfer of the bending stress. Now, if we use those kind of sections for a beam where it is subjected to load and thereby they are subjected to the bending moment and the shearing force, then what is the consequence of shearing stress on such particular sections? Now, this is the kind of a section, I section shown over here. The width of his now this part of the beam we call this as flange, and consequently this is also flange, and the part which connects these two flanges, the vertical one, we call this as web. Now, the width of the flange is B and the thickness is h minus h 1 by 2. Now, this distance is h by 2 and this distance is h 1 by 2. So, thereby this distance is h by 2 minus h 1 by 2. Now, if we are interested to evaluate the shearing stress at any cross section which is at a distance of y 1 from the neutral axis, then as we have seen that we need to calculate the moment of this area which is above the section where we are considering the shearing stress. Now, please note over here that when we have computed the shear formula, we have assumed that the shear stress is uniform across the width. Now, here in this kind of section where the, and also we have said that if the width becomes larger, then the shear stress is no longer uniform over the width, and if you use this formula, it is expected that the results which we are going to get will be erroneous. Now, here since the width of the flange is substantially large in comparison to the width of this web, in addition to the vertical shear which we have in the flange, we get the horizontal shear also as shown over here. Now, because of this horizontal shear, the shearing stress distribution in the flange part is not uniform, and consequently, if we apply the shear formula for evaluating the shear stress in the flange zone, then it is going to be ineffective or erroneous. So, when we evaluate the shear stress in I cross sections, what we do is that we calculate the shearing stress for the web part only, and in fact, you will notice that the maximum percentage of the shear force is being carried by the web, and in the process the whole section becomes effective in carrying the bending and the shear. In case of bending, we have observed that if we have two rectangular components at the top and the bottom, they are effective in carrying the bending stress. Now, what we observe is that if the web part is introduced, that is effective in carrying shearing stress. So, the whole section in combination now is effective in carrying the bending and the shearing actions. Now, so what we do is that this web part, which is similar to that of a rectangular section, in this we compute the shearing stress and we calculate how is the distribution of the shearing stress, which is going to be something like this, a parabolic distribution. You will have the maximum value here, which is tau max, and this is going to be tau minimum. Now, since we are evaluating the shear stress at this cross section, which is at a distance of y 1 from the neutral axis, so we take the moment of this particular part of the area. Now, we divide this part in two segments, this we call as rectangle 1 and this part we call as rectangle 2. Now, for rectangle 1, the area is like this, the width is b and thickness is h by 2 minus h 1 by 2. Hence, this is the area A 1. For the second part, area A 2 is equals to the thickness T multiplied by this is the h 1 by 2 minus y 1 is this particular depth, and consequently as you know q is equals to a y bar. So, for the first rectangle y bar will be equals to this is h by 2 minus h 1 by 2 is the thickness, and half of that, half of h by 2 minus h 1 by 2 is the distance of C g from the top or the bottom, and to that if I add this particular distance which is h 1 by 2. So, this plus h 1 by 2 will give me the y bar of the first rectangle, and for the second rectangle the distance again is h by 2 is this and h 1 by 2 is this. So, this distance is h 1 by 2 minus y 1. So, h 1 by 2 minus y 1, half of that is the C g distance, plus if we add y 1 to that, this will give me the y bar for the second rectangle. So, if you do that A 1 multiplied by this y bar and A 2 multiplied by this y bar, we will get the value of q, which is given by this. Now, in this particular expression, if you note that except this particular y 1 square, everything else is constant. Hence, the shear stress varies again with respect to y 1 and in a parabolic manner, in a square quadratic form of y 1. So, if y 1 becomes 0, then we get the maximum value of the shearing strength and rather shearing stress, and when y 1 equals to h 1 by 2, that gives us the minimum value of the shearing stress, and this is what is the distribution shown over here. So, we will get the maximum shear stress over here, and this will give us the value of the minimum shearing strength. Now, at this particular section you can appreciate that since we have said the shearing stress is 0 on the surface of the section. So, if you look into the bottom part of this beam at this section, here the shearing stress is 0 and at this particular section shearing stress is minimum. Hence, at this particular cross section there is a complex distribution of the shearing stress, and as a result we cannot apply the shear formula for evaluating the shearing stress in the flange zone. So, this is how we compute. So, we restrict ourselves to the wave part and we calculate the shearing strength, and we will see consequently that the maximum shearing stress is being carried by the wave part only. And hence, if we like to compute that what is the value of the shearing force the wave is going to carry, that is equals to the area of the stress diagram we get over the wave part, that is multiplied by the thickness of the wave will give us the value of the shearing force that the wave is going to carry out of the total shear force that the section will be subjected to. Well, these are the values of I of the cross section, which is the b h cube by 12 is for the whole section minus the two sides of it b minus t h 1 cube by 12. So, this is the value of the moment of inertia I, and thereby the shearing stress T is equals to V q by I t, where T is the width of the wave part and this is the q of the section above the neutral axis, and this is the value of the shearing stress that we are going to get. And since y 1 varies, we get the variation from the bottom part to the top part. Well, now let us look into some of the examples based on this. That the first one, in fact, this particular example I had given to you last time for looking into the solution of it. I hope you could solve it. Let us discuss again, so that you can check up your solution with that. Now, the beam is subjected to loads P as shown over here. It is a 2-point loading and they are placed equidistant from the two sides at one distance of 1 meter. Now, you will have to determine the maximum allowable value of P if limiting value of bending stress is 60 MPa and limiting value of shearing stress is 10 MPa. The cross section of the beam is a rectangular one. Now, please note over here that you will have to find out the maximum value of P in such a way that the bending stress does not exceed a allowable limit and consequently the shearing stress also does not exceed the allowable limit. So, you will have to satisfy both the criteria, and satisfying both the criteria, you will have to prescribe that how much load you can apply in this particular form, so that the stresses are not exceeded. Now, you can appreciate from this, since we are going to deal with the maximum possible value of the bending stress and the shear stress that will be generated on this section. Hence, we need to know the variation of the bending moment and the shear force along the length of the beam, and thereby we need to compute the bending moment and shear force diagram, so that we can find out that what is the value of the maximum bending moment and the maximum shear force that is occurring at any point in the beam, and consequently we can compute the value of the stresses. So, if we compute the bending moment and shear force diagram, as we have seen, the first step is to evaluate the unknown reactive forces. Let us call that this beam is A and B, and end A is on hinge. So, you have a vertical force R A and a horizontal force H A, and vertical force at B as R B, they are the reactive forces. Now, summation of horizontal forces equals to 0 will give you H A as equals to 0. Now, we can compute the value of R A and R B. Now, again, since this is a symmetrical beam with the symmetrical loading, so R A equals to R B will be equals to P, and this you have seen earlier as well. Now, with these values of the reactive forces, we can compute the shearing force at any cross section, and we can draw the shear force diagram, and the shear force diagram is going to be like this. That means, over the left region between the support and the load, we will have a shear force of magnitude P kilonewton, which is negative, and between the second load point and the last reaction, we will have again P kilonewton, which is positive. So, the maximum value of the shear force that is occurring anywhere in the beam is equals to P kilonewton, and in between the loads there are no shear force at all. So, the maximum shear force is equals to P kilonewton. Consequently, if you draw the bending moment diagram, you will find that the bending moment at these two supports is 0, and the moment value here is going to be equals to P into 1, which is P kilonewton meter, and over this it is constant. Since the bending moment is constant over this zone, hence the shear is 0 over here. Now, the maximum value of the bending moment that you get is equals to P kilonewton meter, and that is occurring at the load point, and maximum shear force is occurring between the support and the load point. So, if we look into that this is the maximum shear force and this is the maximum bending moment. Now, as we know that the bending stress is equals to sigma, which is equals to m y by I, and where m is the bending moment or the maximum bending moment that is acting in the beam, y is the furthest point from the neutral axis, which will give you the maximum stress either top or the bottom, and I is the moment of inertia of the cross section with respect to the neutral axis. Now, as we know that for rectangular section, I is equals to B h cube by 12, and y furthest distance is h by 2. So, this is 2 by h. So, this is going to be equals to B h square by 6. So, I by y is equals to B h square by 6, and if you substitute the values, you get this value of B h square by 6. Now, the bending stress is limited to 60 MPa, and m we know as P kilonewton meter. So, if we substitute these values of the stress, the P and I by y, which is 100 times 250 square by 6, from this we get the value of P as equals to 62.5 kilonewton. So, from the maximum bending stress criteria, we get the value of P as equals to 62.5 kilonewton. Now, let us look into the value of P which we get if we have to satisfy the maximum shearing stress criteria. Now, as we know that the maximum shear stress in a rectangular cross section occurs again at the neutral axis, since it varies parabolically, and the maximum value which we get is equals to 3 V by twice A. Now, maximum allowable shear stress is equals to 10 megapascal. V we have obtained as P, maximum value of V, and cross sectional area is 100 times 250. So, if we compute this from this, the value of P, it comes out to be 166.7 kilonewton. So, now that you have two values of P and you will have to choose the most appropriate one. Now, if you use the higher value of these two, P equals to 166.7 kilonewton, if we use that value, then the bending stress is going to be go beyond the 60 megapascal, that is the limiting value, because we have obtained the value of P corresponding to the bending stress as equals to 62.5 kilonewton. And if we use 62.5 kilonewton as the loading, then shearing stress will be lower than 10 megapascal, since we cannot go beyond the allowable limit of the stresses. So, we will have to use the lower value of the P, so that both the stress criteria, bending stress and the shearing stress, they are satisfied and the member is safe against this loading. Hence, the value of the P which should be used is equals to 62.5 kilonewton. Now, let us look into another example problem in which is the application of the shearing stress. Now, here and of course, with a different cross section than a rectangular one. Now, the maximum vertical shear force acting on this beam cross section is given as 100 kilonewton. Now, the shearing force has been computed for you. The cross section of the beam, as we can see, is an I section. The value of the shear force, maximum shear force, is known. Now, that we will have to compute that what is the maximum shearing stress that is occurring in this particular section, and how much shear force is going to be carried by the web out of the total shear force that will be coming in this particular cross section. So, these are the two aspects we will have to compute, the maximum shear stress acting on this particular section and then percentage of shear force that will be carried by the web of this beam. Now, the cross section of this is an I section and this is a symmetrical one. So, the position of the neutral axis will divide the section in two equal half. So, this is the position of the neutral axis and we got to compute. So, the maximum value of the shear stress, as we have seen, will be acting at the neutral axis location. So, we got to compute that value of the maximum shearing stress first. Now, if we like to compute that, we can compute in this form. That means, we compute the value of the Q for evaluating the shearing stress at this particular location. Now, since we are considering this particular section, so the area above this is to be considered for evaluating the first moment, which is Q, Q equals to A y bar. Now, also we need to compute the shearing stress at this particular location, because we need to compute the value of the shearing stress in the web, as flanges we cannot calculate the shearing stress in the flanges using this shear formula. So, when we will be computing the shearing stress at this particular location, the area to be considered is this particular part. So, that is why the value of the Q's will be different for evaluating the shearing stress here and the shearing stress here. Now, when we are going to compute the shearing stress at this particular location, then we have two rectangular component. One is the width 200 multiplied by 20. So, 200 times 20 into the distance of its CG from the neutral axis. Now, distance of its CG from the top is 10. So, this is 120 from here to the neutral axis is 120. So, 120 minus 10 is 110, and for the second rectangle the area is 20 times 100. So, 100 into 20 is the area and its CG distance from the neutral axis is 50. So, Q for the first part, that means for this particular section when we are evaluating the stress where the shearing stress is maximum. So, for tau max this is the value of the Q, and if you compute this, it comes this as 54 into 10 to the power 4 millimeter cube. Now, this is Q is A y bar. Now, unit of A is millimeter square and y bar is millimeter, hence this is millimeter cube. Now, for computing the minimum shear stress tau minimum, which is at this particular section, the area to be considered for Q is the area above this particular section, which is this rectangle alone, and area of this rectangle is 200 is the width, 20 is the thickness, and 110 is the distance of its CG from the neutral axis, because 120 is the distance from the neutral axis to the top minus the CG distance from the top to this CG, which is 10, equals to 110. So, Q for the top rectangle only is equals to this, which is required for evaluation of the minimum shearing stress. Now, as we know that tau, the shearing stress is equals to V q by I b, and I of this particular section is, if we consider the whole thing as one rectangle and if we compute the moment of inertia with respect to this axis neutral axis, then 200 and height is 220 plus 20 240. So, 200 into 240 cube by 12 for the entire rectangle, minus we subtract this particular part which is this width minus this width, which is 200 minus 20 equals to 180 times this height which is 200. So, 180 times 200 cube by 12, if we subtract that, then we get for this I section, and this comes out to be 1110.4 into 10 to the power 6 millimeter to the power 4. So, this is the value of the moment of inertia I. Now, if we compute the maximum shear stress, the Q which is to be used is this. So, shearing value is 100 kilonewtons times 10 to the power 3 so much of Newton, 54 into 10 to the power 4 is Q, and I is 110.4 into 10 to the power 6 multiplied by T which is 20, and this gives us a value of 24.5 MPa. Consequently, so this is the maximum shearing stress at the neutral axis position. So, this is the value of the maximum shear stress. So, this is tau max, this is tau max. Now, the minimum shear stress which is at this particular location is given by this expression, again V q by I b, and only there is a change in the value of q which is 44 into 10 to the power 4, and thereby we get a stress of 19.93 megapascal which is at this particular location. So, this is the value of tau minimum. So, this is the first part that we compute the maximum stress and the minimum stress. So, this is the maximum value of the shearing stress that will be occurring in the beam section when they are subjected to a shear force of 100 kilonewton, and in this particular I section the maximum value of the shear stress is at the neutral axis and the magnitude of that is 24.5 megapascal. Now, let us look into the second aspect of it, in which we need to find out that how much shear force out of this 100 kilonewton the wave part of this beam is going to carry. Now, since this is the shear stress distribution over the wave of the beam, so the force as we know is equals to stress times area. So, if we take the area of this shear stress multiplied by the thickness, that will give us the shear force that will be carried by the wave. So, the shear force this is by wave, the shear force which is being carried by the wave is equals to the thickness of the wave multiplied by the area of the stress diagram. Now, this area of the stress diagram we can divide the whole stress in two parts. If we look into that, we have a stress distribution is something like this. Now, we can divide this into two parts, one is this rectangular part and another one is this parabolic distribution. Now, this value is tau minimum and this is height h which is equals to 200. So, 200 times 19.93, the minimum value of the shearing stress is this particular rectangular area, and this parabolic area will be 2/3 of this height times this distance. Now, this distance is the tau maximum minus tau minimum, that means 24.5 minus 19.93 will give us a value of 4.57. So, 2/3 of 200 times 4.57 is the area of this parabolic part. So, this gives us the whole thing gives us the area of this entire stress diagram. When that is multiplied with the thickness, we get the value of the shearing force, and this turns out to be 92 kilonewton. So, please note over here that out of the 100 kilonewton shear force that the entire cross section is subjected to, out of that 92 kilonewton shear force is being carried by the wave alone. Hence, the 92% of the shearing stress, total shearing force is being carried by the wave. So, this is interesting to note that as we had seen earlier, that this section is really effective because the top and the bottom rectangles which we have called as flange, these flanges are effective in carrying the bending stress, whereas this wave is quite effective in carrying the shearing stress, because 92% of the shear force is being carried by this particular wave. Hence, in fact, in normal design, in our engineering design, what we do is that we assume, where we do not really need to compute the stresses that precisely, we assume that the shearing stress is being carried by the wave alone and the bending stresses are being carried by the flanges of this section, and this is quite interesting, and that simplifies the calculation to a great extent. Now, let us look into another example where we have a beam and it is loaded in this particular form, and the loads are that you have P at the two ends and 4 P at the center. Now, this particular beam is hinged at this particular end, let us call say this as A, this end as B, this point as C, this is D and this is E. So, it is hinged at B and on roller support at D, overhang between B and A and D and E, and this is the loading it has. Now, the cross section of this particular beam here is similar to that of like a T section. Also, as we have discussed in case of I sections, that we cannot use a shear formula for evaluating the shear stress in the flanges of the I beam. For T sections also, if we compute the shearing stress in the flange using the shear formula, is not going to be accurate or correct. Hence, we restrict ourselves to evaluation of the shearing stress only in the wave part of the beam. So, here also the top part we call as the flange of the T beam or the T cross section, and this we call as the wave part of the T cross section. Now, here the neutral axis position is given, which is at a distance of 70 millimeter from the top of the beam, and the moment of inertia of this particular cross section also is given over here. Now, what we need to know is that maximum safe value of P, so that the shearing stress does not exceed beyond this allowable stress limit 6 megapascal. Now, in this particular problem, as you can see here, it has been stipulated that the maximum shear stress that is allowed is 6 megapascal, and it is silent about the maximum allowable bending stress. So, since it is not indicated anything with regard to the bending stress, so we compare our actual stress, that is our actual shearing stress that is going to happen in the beam because of such loading, and that if we equate to the maximum allowable shearing stress, then we can find out what is the value of P that we need to limit to, so that the shearing stress does not go beyond the 6 megapascal value. Now, to compute that, let us look into the shear force diagram of this particular beam, and as usual we compute the value of the reactive forces R B and R C as we have discussed, R D as we have discussed earlier, and this is going to be the shear force diagram. Now, as you can see that the maximum value of the shear force which we have is equals to twice P, and this is the maximum value of the shearing force which is indicated over here, and the value of the moment of inertia is already given. Now, as we have seen that in case of the rectangular sections we get maximum shear stress at the neutral axis. So, for this rectangular component, now at this particular section our shearing stress is not 0, but you will have some value which we call as tau minimum for this, because you have some area for which you get the Q value which is A y bar. Now, when we had taken the rectangular section, above the rectangular part, the top surface, we did not have anything, and that was the value of the 0 shear stress. Now, here when we are considering the T sections or the I sections, now above the wave we have the flange area which is contributing to the first moment of area which is Q, but we are calculating the shearing stress from the interface and downward. So, we have some value of the shearing stress at the interface between the wave and the flange, and that we are calling as the minimum shearing stress tau minimum. So, if we compute the value of the maximum shearing stress at the neutral axis, then again from tau is equals to V Q by I T, V is known now which is 2 P, Q is equals to A y bar which is above this neutral axis, and this is what is Q. Now, here we have two rectangles, one is 80 times 20 and the distance of C g from the neutral axis is 70 minus 10 which is 60. Second rectangle is 50 times 20 and the distance of C g from the neutral axis is 25, and this gives us a value of 121 into 10 to the power 3 so much of millimeter cube is the value of Q, and I we know. So, if we substitute this value and T is equals to 20, if we substitute these values we get the value of P as 77 kilonewton. So, the maximum value of P which can be applied in this beam is equals to 77 kilonewton. So, that the shearing stress does not exceed a value of 6 megapascal as stipulated over here. Well, now let us look into this particular problem which has relevance with the discussions we had today, that the cross section of this particular pole, in fact, this is a wooden pole having a solid circular section of diameter d, and this is subjected to a lateral load of 2.5 kilonewton at the top. Now, as you can make out that this particular member, when it is subjected to this load, you can orient this and take this as a cantilever beam subjected to a load at its tip, which is of value 2.5 kilonewton, and this length is equals to twice 2 meters. Now, what we will have to do is that we will have to determine the diameter of this particular pole, so that the stress in bending does not exceed 20 MPa and the stress in shear does not exceed 5 MPa. Now, if we do that, if we draw the bending moment and shear force diagram for this particular pole, then the bending moment and shear force diagram is going to be like this, which you know we have already done earlier. So, the maximum shear force is going to be equals to 2.5 kilonewton and maximum bending moment is going to be equals to 5 kilonewton meter. Now, if we compute the bending stress from this particular expression, which is equals to sigma equals to my by I. Now, maximum bending moment is 5 kilonewton meter. Now, here the moment of inertia with respect to this neutral axis is equals to pi d4 by 64, and the extreme distance which is from the neutral axis is at a d by 2, and that is the point where you are going to get the maximum bending stress. So, I by y is equals to pi d4 by pi d cube by 32, and if we substitute these values limiting the bending stress to 20 MPa, we get the diameter of this particular pole as 136.6 millimeter, and corresponding to the maximum shear force of 2.5 kilonewton. And as you know that we are interested to evaluate the maximum shearing stress, as we cannot compute the shearing stress at any other point in this particular circular cross section. So, tau max is equals to 4/3 V by A, as we have seen, and if we substitute the limiting value of the shearing stress from this particular expression, we get the value of d as equals to 29.14 millimeter. Now, out of these two values, where corresponding to bending we have d as equals to 136.6 millimeter, corresponding to shear we have 29.14 millimeter. So, naturally we will have to go for the larger diameter, so that it can withstand both the stresses. If we provide the lower diameter, then it will be safe against shear, but it will not be safe against bending. However, if we go for the larger diameter, then it will satisfy both the criteria. Hence, the diameter of the pole has to be minimum as 136.6 millimeter, so that it can withstand both the stresses or withstand this amount of load, so that the bending stress and shear stresses are within limits. Well, this is another problem which is again the cross section of the beam is just like a T. Now, here two rectangular components are there, one rectangle is the top one, another one is the bottom one, and these two rectangular sections are interconnected along the length by using nails, and these nails are spaced at a particular spacing. Now, that particular spacing we will have to find out, so that the stress, we know the shearing capacity of these bolts, that these bolts are subjected to this much of shearing load, that 872 Newton is the shear force that the particular cross section is subjected to, and the nail has a shearing capacity which is 400 Newton. Then you got to evaluate the spacing, so that these particular bolts do not fail against the shearing stress. Well, this particular problem is given to you, we will discuss next time, and you try to solve this problem and see whether you can get the results. Well, now to summarize what we have discussed in this particular section or in this particular lesson is that we have recapitulated the previous lesson. We have introduced the concept of shear stress in beams with different cross sections other than the rectangular one. In the previous case, we had discussed about a cross section where the cross section is a rectangular one, but here we have discussed about the circular or T or I sections, and then effect of shear strains on longitudinal strain in beams. Also, we have looked into some examples to evaluate shear stresses in beams. Now, in fact, this is the last lesson in this particular module. So, in this module of stresses in beams, which consists of 4 lessons, we have divided into 2 parts. first two lessons are devoted on the aspects of bending stresses, and the last two lessons, the third and fourth, we have devoted on the aspects of the shearing stresses, and thereby we have seen the effects of the loads in terms of bending and shearing stresses in beams. Well, these are the questions set for you, that in a beam with rectangular cross section, what is the maximum value of shear stress and where does it occur? In a beam with circular cross section, what is the maximum value of shear stress and what is meant by average shear stress? Now, while discussing, you have looked into that, we come across a term which we call as the average shear stress. Now, what really we mean by average shear stress? So, look into these questions and try to find answers for this. We will discuss these questions in the next lesson. Thank you very much.